This is a lecture on mixing problems, and in this lecture I will show you how to set up and solve two mixing problems, one with the volume in the tank constant and the other with the volume in the tank variable. There are quite a few variables in these problems, so let's look first at algebra. In algebra you had various volumes of substances with certain concentrations in them, and you mix them together to get a final substance. So V is volume, C is concentration, Y is the amount of the dissolved substance. Of course, these are related. The amount equals the concentration times volume, so Y equals CV. Then you have two continuity equations. One is that the amount of the volumes have to stay constant. If you mix volume 1 plus volume 2, you're going to get volume 3, and then the amount so Y, this is really Y1 plus Y2 equals Y3. Now algebra is fine in the static case. Say you need to make a mixture with so much concentration, so many milligrams per kilogram of some dissolved substance, and you need 4 cc's of it, and you have other concentrations and other volumes, and how do you mix those together? That's the algebra problem. Now there's several levels to the more dynamic problem, and these require differential equations. So if you say that the amount that's being added is added over time, and say you have a tank and the amount taken off is taken off over time, then you have the problem that we're going to set up now. But we are going to make another assumption with it. We're going to assume that when the mixing occurs in the tank, it occurs all at once. If you want to study the problem of putting some substance in the tank and then watching it diffuse across the tank to the output, that requires a numerical model. So for the differential equations, we're going to have the same variables, only they're going to be functions of time. Volume is a function of time, concentration, and the amount of dissolved substance. They're all functions of time now. So basically we have the idea that the rate of change of the amount of substance in the tank equals the amount that's put in, the change in the amount that's put in, minus dy by dt, the amount that's going out. Just sort of a continuity equation there on the amount of the substance, or the rate of change of the amount of the substance. So if I use that the amount equals concentration times volume, put that through this differential equation, I get something that's totally intractable. I mean, it's got many derivatives, so we'll make quite a few assumptions and we'll simplify this down. This is typically what's done in the mixing problems in differential equation classes. Again, if you really want to do a true mixing problem, you would do a numerical solution on a computer, and that would include diffusion and all sorts of other things. Let's draw a picture here of what we're talking about. So we have a tank here, and we have some kind of input, and somewhere around here there's a hole, and we have an output and a certain volume in the tank. Okay, that's what we're talking about. And let's say that the concentration in this input stream is constant, so this term is 0, and the concentration in the output stream is constant. Let's set this one to 0. And now let's say that the rate that the volume is, the rate in this input and the rate in the output are constant. So we can call these constants. This can be R in, and this can be R out. And now we just have a differential equation in terms of Y, and that is the amount of substance in the tank. So we can get rid of the word tank. And now we have some differential equation that we can actually solve. Now, I didn't mention a few other assumptions. We're also going to assume that the volume in the tank, any changes that are due to that input and output flows, and not to leaks, not to any evaporation. So we can say the volume in the tank here equals the initial volume in the tank plus the input rate, input change in volume times time, minus what's going through the output. Well, we can write it like this. And now here's our differential equation. dy by dt, y being the amount of substance in the tank, equals the input concentration times the input rate minus the output rate divided by this continuity for volume times y of t. And it's an initial value problem. We can write the initial amount in the tank at time 0 is y naught. Now there are two problems here. If the input and output rates are the same, then obviously this term is gone, and we have the volume in the tank never changes. What the amount put in is equal to the amount taken off, so the volume's the same, which is its initial amount. Now this is case 1. So we'll solve this one, and then we'll go back and solve the one, the case where the input and output rates are different. So the equation we wrote was a first order linear autonomous differential equation. It isn't separable, but it can be solved by means of an integrating factor. Actually, this one is separable. Sorry about that, but we're going to use an integrating factor anyway. Okay, so here we go. We'll write it in standard form. Okay, if you remember standard form, it's like this. dy by dt equals some function plus some function of, we'll call p of t times y equals some q of t. And here's the q and here's the p. Now you can refer to the lecture on integrating factor. I'm just going to take ideas from it. The integrating factor is e to the integral of pt dt. Well, this is a constant, so you have the integral of r n over v naught times t dt. Oh, dt, I'm sorry, there's no t in there. That's just e to the rn over v0 times t. So that's the integrating factor. Now when you create the solution, you can rederive the equations, or I don't know, to me it's just as easy to remember it. You have the integrating factor with the negative sign times the integral of the integrating factor times q of t. So in this case we have e to the minus rn over v0 times t times the integral of q of t, which is right here, here's q of t right here, times the integrating factor. This integral is easy. All you're really integrating, since this is these are constants, all you're integrating is this exponential, which is easy to do. And here's the answer. Okay, well first remember you take the integral and then you have to multiply through by this exponential. So the exponential times this one will give you a 1, but the exponential with the negative sign times c will give you this final term out here. So we end up with the input concentration times the volume in the tank plus constant of integration c times this decaying exponential. Now we have an initial condition that y at time 0 was y0, so we can put a 0 through this equation and we get c in v naught plus c, because this exponential goes to 1 when t is 0, and we can solve for the concentration in the tank, and we will get a solution that's similar to the solutions we have seen previously. So here's the solution. You think I'd learn that the default is that square instead of the pin, but I guess not. Alright, we have a constant term. This is our steady state term. Then we have a transient. The transient's right here. It's a decaying exponential. You can see from how this is written that this equilibrium will be stable. The steady state is the equilibrium. If you put this value into the original differential equation, okay, you end up with 0. Remember, an equilibrium solution is one for which dy by dt equals 0, and we put the steady state into that differential equation, we end up with 0, showing that the steady state and the equilibrium are the same. Now, but because of the behavior of the transient, this equilibrium is also a stable equilibrium. It means if the concentration in the tank is above what's being supplied to it, eventually that concentration is going to reduce down asymptotically, approach the concentration in the input flow. If the concentration in the tank is lower than the input concentration, you keep pouring in and taking off at the same rate, eventually the concentration in the tank will be the same as the input. So now that we solved in general, we can do a specific case and evaluate some of the numbers. Let's say we start out with a tank that contains 2,000 liters and it's full. And it has an initial concentration of 14 milligrams per liter in those 2,000 liters, giving initial amount in the tank is 28 kilograms. Now solution is going to be added at the rate of 3 kilograms per liter, and it's there, but the rate is going to be 10 liters per minute entering and leaving, so that Rn and Rat are the same. That's why this is a constant volume problem. We can run those numbers through and you'll see right here, here is your equilibrium amount in the tank, 6,000, because the concentrations are going to be equal but the amount will be different. All right, here's the transient term, and if you write, remember, e to the minus t over tau gives you sort of a half-life, or time constant rather, and in this case you would have to do e to the minus t divided by, and it would be v0 over Rn to get a time constant. The time constant turns out to be 20, in this case 20 minutes, because of the rate that we used rates in minutes. So if you use the rule of thumb that in 5 time constants an decaying exponential is essentially over, that means that about 5 times 20, which is 100 minutes, you should be very close to the concentration. And we will see that on the graph on the next slide. And here's the result from the mixing problem. We started off with 28 kilograms of some dissolved substance in this tank of 2,000 liters, a 2,000 liter tank, right? In about 100 minutes we have approached we're fairly close to the equilibrium value of 6,000. You can also run this in kilograms per liter, remember, by dividing by volume, and the equilibrium amount then would be 3. Now we'll do the other problem. Now we're going to look at the case in which the tank volume isn't constant. It's not constant because the input rate is not equal to the output rate. So if the output rate is higher than the input rate, you'd be draining the tank. If the input rate is higher, you're going to be filling it, but you can only fill it to the point where it's overflowing, and then you don't have the same, you have to stop the problem, the calculation. So here is the equation before. Remember, in the previous case, this was all set to 0 because the two were equal, and that gave the constant volume. Here it's non-constant, we have to leave this term in. It's still in standard form written here, and it can be solved by use of an integrating factor. In this case it's not separable because you have this function of t and you can't separate it from the other terms. Now here's the integrating factor, but I want to point out something that we're used to seeing, these exponential integrating factors. This one is not exponential. So if I take this integral that's up here in the exponent and carry that out, I end up with a natural log. The e raised to this horrendous expression, remember that e and natural log are inverses of each other, so they cancel because you have to take the exponent and put it over here using the laws of exponents, or the logarithms. And now you end up with no exponent, okay? No e in the integrating factor. That's a little unusual, but I just wanted to point out that we're doing a problem that's just a little different here. So this is a case in which your integrating factor does not contain e to the some exponent. Here's a solution again. If you run that exponent, the integrating factor again with a negative on it, I guess I'll never learn that. Okay, you'll get a negative in that exponent here. So you're multiplying by it. These are your constants, that q of t. Here is the integrating factor again. And now you want to carry this out. It looks fairly horrendous, but you can make this substitution. Here's a u substitution, and you can work through that. And you get something that doesn't look too bad, right, which you can integrate and then reverse the u substitution. So when I evaluate it, this is what I get for an integral. Remember, you're going to multiply through here. Again, I have a constant of integration c. I'm going to go ahead and reverse the substitution at this point, and this is what I get. Then I can use the initial condition to evaluate the constant of integration. This is all standard, just requires some algebra. And now we can write the solution for a mixing problem for a non-constant tank volume. And now we've got, it's autonomous, things are changing with time, so we don't really have a steady state like we had before. But we do have a different problem. We can only fill this tank to where it's overflowing or until it's empty. So let's look at that. So here's a case, we'll again use the 2,000 liter tank that we did before, but we'll only have it half full, so it only has 1,000 liters in it. So we have an initial concentration of salt of 14 as before, but the initial amount in the tank is less than previously because there's only half the volume in it with the same concentration. I'm comparing this to case 1 that we did earlier. And now we'll have the same input concentration of 3 kilograms per liter, but it's entering the tank at 10 and leaving at 8. So we have to worry that we're going to get to the overflowing problem. Now the volume has to stay at 2,000 liters. So we can solve for t, the time at which you get from the 1,000 to the 2,000 liters, and that's going to take some time, 500 minutes, but at that point you have to stop the calculation. And here's the result. Again, we have a 2,000 liter tank, initially at 1,000 liters. At this point, at this time, the tank is overflowing, it's full. Right, we started with 14 kilograms in the tank, which was a lower concentration or lower amount than before because we only had 1,000 liters in the tank. You can see the curve looks a little bit different than before, and we had to stop the calculation before we got closer to the equilibrium amount of 6,000. So those are your two mixing problems. The book has the mixing problems sort of scattered throughout the book. I'm put them all together in one lecture, so you have them all here in the written lecture and also in the video, and you can trace through the steps. So these were good examples of using the integrating factor for solving differential equations and obtaining closed form solutions.